This is Honors Geometry Section 6.5 on rhombi and squares. Rhombi is the plural for rhombus. We're going to start off with the definition for rhombus. A rhombus is a quadrilateral with four congruent sides. In other words, it would be considered equilateral. And since all four sides are congruent, that also means that both pairs of opposite sides are congruent, which means we could also classify it as a parallelogram. In fact, it's a more specific type of a parallelogram. The rhombus has certain properties. Here's a rhombus. I can draw in those two diagonals in green. And because this rhombus would also be considered a parallelogram, we know that the parallel sides, or the opposite sides, are parallel to each other, so those alternate interior angles are equal to each other. Additionally, we would be able to prove that this triangle is congruent to this triangle by side, side, side. Those triangles are congruent to each other, which isn't anything unique. However, the way we could match it up is that triangle ABC is congruent to triangle ADC. In other words, the corresponding parts would be this angle congruent to that angle, and this angle would be congruent to that angle. And then by a transitive, we would be able to say that this angle 1 is congruent to that angle 2. What that allows us to do is then look at trying to prove this yellow triangle congruent to this pink triangle. If I look at the comparison between them, I have a pair of sides, I have a pair of angles, and going back to the fact that this rhombus is also a parallelogram, the diagonals bisect each other, so this segment is congruent to this segment. In other words, yes, those triangles are congruent to each other. Since those triangles are congruent to each other, that means angle 3 is congruent to angle 4. Since those angles are congruent and form a linear pair, so they're supplementary, it means 3 and 4 must also then be both right angles, which leads us to the special properties of a rhombus. Number 1, diagonals are perpendicular. Number 2, diagonals bisect the vertices. Next, we'll look at the ways to prove that something is a rhombus. First of all, there's the definition. If we can get all four sides congruent, then we can say it's a rhombus. Or if we know it's a rhombus, then we can use that definition in the other direction and say that all four of the sides are congruent to each other. Another way to prove rhombus is to prove that it is, first of all, a parallelogram, and also that the diagonals are perpendicular to each other. If you know that, then you could say that the shape is, in fact, a rhombus. The third way is to prove, once again, that it's a parallelogram, and also that the diagonals bisect one of the vertices. If that's the case, then once again we can conclude that it is a rhombus. And our third one is to get that if it's a parallelogram and you have a pair of consecutive sides are congruent, that means that opposite sides are congruent, so all the sides are congruent, so once again that must be, in fact, a rhombus. Back to these markings, all four of those sides are congruent. Here's an example of proving that something is a rhombus. First of all, we have the given, and since TU is parallel to RK and TK is parallel to UR, we can say that using the definition of a parallelogram that TURK is a parallelogram. And since it's a parallelogram, and we have consecutive sides of TU and UR that are equal to each other, then we can conclude that TURK must be, in fact, a rhombus. Next up, we'll look at a square. Definition of a square is that it is a quadrilateral that has four congruent sides and four right angles. So if you can prove both of those things, then we can say, in fact, that it is a square. Another way to prove it, which is virtually the same thing, with just slightly different terminology, if you can prove that you have a rhombus and also that you have a rectangle, that implies that the shape you're working with must in fact be a square. So you could use either one of those methods to establish that quadrilateral is a square. Here's a proof proving that something is a square. First of all, what they're given, we have that TY is parallel to OM, TY is equal to OM. So with that, after we've claimed the given, we can say that TOMY is a parallelogram since we have one pair of sides that are parallel and congruent. Next, segment TM is equal to segment TO, which is congruent to segment OY, and that means that we can say that this is a rectangle since it's a parallelogram and we have congruent diagonals and it is a rectangle. The next thing we have is that segment TM is perpendicular to segment OY Because of that, we can say that it's a rhombus. Since it was a parallelogram and we have perpendicular diagonals, then we can say that this is a rhombus. So in conclusion, since it is both a rectangle and a rhombus, we can conclude TOMY is a square. Now we'll move into some coordinate problems, and the directions are to classify this. So we have these 4 points. They're put over onto the graph, and the quickest way for me to try to start classifying this as specifically as possible is to start going after the slopes. So first of all, calculate the slope of RF. 5 minus 2 over 1 minus 3 is negative 3/2. And RF is opposite of segment NE, so we'll look at NE next. 4 minus 7 is negative 3, 6 minus 4 is 2, so since they have the same slope, I know that RF and NE are parallel to each other. Going a little bit further with that, the slope formula has y2 minus y1 over x2 minus x1. The distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So I'm not simplifying these down, I'm just squaring the numerator, squaring the denominator, and I get that RF is the square root of 13. For that same reason, the length of NE is also equal to the square root of 13, so those two sides have an equal length. And right now, I know since those sides are parallel and congruent, it must at least be a parallelogram. Going further, I'm going to look at the other sides. We'll look at segment RN, calculate that slope. 7 minus 5 is 2, 4 minus 1 is 3. And calculating this distance, 9 plus 4 is also root 13. So it's a parallelogram. We have congruent sides, so it's at least a rhombus. And the other thing I'm going to look at is that since RN and NE have opposite reciprocal slopes, that means I know that we have a right angle there. It's perpendicular, so since it was a parallelogram and a right angle, they're all right angles, and it is a rectangle. Rectangle and rhombus together means the best name for this shape is square. Here's our next example. We have the points AN, DY. Once again, we're going to calculate slopes. I'll start with the slope of segment AD, 0 minus negative 3, negative 3 minus negative 7. And then opposite of AD is YN, so the slope of YN is going to be 4 minus 1, 3, 0 minus negative 4, 4. So segment AD and segment YN are parallel to each other. If I were to calculate these lengths, the length of AD is the square root of 9 plus 16. And then the length of YN is the square root of 9 plus 16 also. That would simplify down to 5, but the most important thing for me is to realize that those have the same length, so I know they're congruent, so once again we at least have a parallelogram. I need to do one more side. I'll go after YA. Negative 3 minus 1 is negative 4. Negative 7 minus negative 4 is negative 3. That simplifies to positive 4/3. So comparing these slopes, these are not opposite reciprocals, they're just reciprocals, so they're not perpendicular. However, the length of segment YA is equal to the square root of 16 plus 9, which is also root 25. So YA is congruent to those other ones. It was a parallelogram with consecutive sides congruent. So the best name for this quadrilateral is rhombus. We're doing the same type of problem, but now we're doing the classification with variables. And I don't know where these points are located in terms of which quadrant, what's positive, what's negative. Should GR be going up and to the right? Should it be going down and to the right? We don't know for sure. But we can get an idea of the orientation, G to R to T to A. So we'll go through the same process. Find the slope of GR, 2E minus D minus E minus 2D. So there's Y minus Y over 4D minus D. We'll do the subtraction. That's E plus D over 3D. There is the length of segment GR, or the slope of segment GR. Opposite of GR is AT. So when we're calculating this one, it's 2E minus 4D minus E minus 8D over E plus 5D minus 2E plus 3D. Subtract these. And we get this. So GR and AT do not have the same slopes. So already right now I know this is not going to be anything in the parallelogram family. Those two segments do not have the same slope. So it cannot be a parallelogram, it cannot be a rhombus, it can't be a rectangle, it can't be a square, it can't be any of those. I could do one more check, go for the slope of GA, and also the slope of segment RT. So I've got those all set up to subtract and divide. So for our first one, this comes out to negative 6D over E plus 3D. And for the slope of segment RT, this one's going to come out to negative 3D over E plus D. And none of these segments have the same length. So my best name for this one is just a plain old quadrilateral.